In this recitation, we'll walk you through some basics of audio datasets. In homework 1, we will provide MFCC speech data formatted as NumPy arrays. It is a format of audio data that's derived from raw waveform data. The process of calculating it is not required in this course, but we'll cover that in Recitation 1. Now, after downloading the dataset, you can see the folder structure below. DevClean consists file for testing your model. Test folder contains data that requires you to predict and submit to Kaggle, and train folder is the folder for training. Let's load one training sample to give you a better idea on audio datasets. Here we loaded a speech from DevClean and its transcript. Every speech data is organized as an array of shape t times 28, where t is the total number of time steps for that sample, and 28 is the number of features for MFCC file format. As you can see, for this training sample, we have 581 time steps and 28 features for each time steps. As for the transcript, it is organized as a 1D array with length t plus 2. The two extra time steps are SOS and EOS tokens, which stand for start of sequence and end of sequence, located in the beginning and the end respectively. Note, for homework 1, the two tokens are not needed, so you might want to remove them in part of your pre-processing pipeline. One important technique that we are going to use for homework 1P2 is context information. Proper management of local context is essential to homework 1, in which we are predicting the phoneme for each of the time step. The dominant solution in the past was setting the handcrafted context with the following approaches: derivatives or context windows. In this homework, we are going to apply context windows. Context windows adds a local context by simply concatenating multiple consecutive time steps. The result is a bigger feature vector that is better aware of the local information. For example, originally the input to the network and the expected output to the network for time step 64 would be like this. Now we want to apply context window of 10 to the 64th time step. This could be done by concatenating features from 10 past and 10 feature frames. So we created a new variable x with context, in which we have 11 frames. So after concatenating the context, the shape of x is 21 times 28. Also, since we're designing an MLP network, we might want to flatten x to a 1D array, as it's a single training sample.